In dryland agriculture, monitoring soil salinity is an important task, and one tool available to farmers is the EM38 scanner. In this video, DPIRD hydrologist Russell Speed will guide us through the workings of the EM38 scanner and its practical application in the field.
Okay, so this is called an EM38. It's an electrical conductivity measuring instrument. It's a Canadian made instrument by Geonics in Canada. They make a lot of geophysical equipment that penetrates at different depths. So it's effectively sending out a radio pulse into the ground, and then it's listening for how that radio pulse is reacting in the ground, and conductive material like either minerals or salt will produce a current, or that radio wave will act with the conductive material, produce a current, and then this listens to that return signal. And the strength of that return signal gives an idea of how much conductive material is in the ground. In our landscapes, that's generally salt, like in our Western Australian cropping soils, that's normally salinity. So we can use this for doing shallow surveys of the salt effectively within the topsoil areas. Correct. So this measures conductivity down to, in that mode, in a vertical mode, it'll measure down to about 1.2 metres, with perhaps most of the signal coming from around about 70 centimetres, where most of the signal it would be measuring mostly around about 70 centimetres below the ground. And then we'll also take some readings in what we call the horizontal mode, where the depth of penetration is only as much as half a metre, maybe 50 centimetres below ground, with, say, most of the signal coming from about 30 centimetres below the ground. So in those two modes, it gives us an idea of the salinity profile effectively within the rooting zone of our agricultural crops.
Common salt is one of the things that is accumulated in our agricultural soils. However, to ensure accurate readings from the scanner, there are a few other things that need to be considered when interpreting the readings.
Like common salt is one of the things that has accumulated in our soils. This can't actually discriminate exactly what it's reacting to. So if like salt's commonly what it is, but we'll also find, well, if you've got steel cap boots on, it's going to react to that, any metallic things. But in our agricultural landscapes, if it's not salt, the other thing that can influence the readings is the soil texture. And so sand not really having any conductive properties whatsoever, compared to a clay where there's some clay minerals. Some of the clay minerals have got some conductive capacity, so we're going to get a higher reading in clay than we will in sand as a background reading. And then obviously clays, it compounds a bit, because clays are more likely to hold salt as well, or retain a lot more salt, so fertiliser and the rest of it. So that can compound the reading. So we generally expect higher readings in heavier textured soils to start with, and they also tend to be, for salt accumulation, that's if the salt's going to generally have higher salt readings within the clay profile in the salt affected soils, as opposed to a salt affected sand. Still going to have higher readings, but it's those clays that really dominate our valley floors, and where the worst salinity we see is associated with those heavier soils normally.
At this site near Latham in Western Australia, Russell and the Levy team took readings in a transect in a salt affected area in a paddock. Initial readings were taken in the crop portion of the paddock, then taken progressively towards the valley floor, where a deep drain has been built to divert groundwater, with the aim to prevent further salinity issues. These readings tell an insightful story. In the crop sections, we observed a salinity reading of 65 millisiemens per metre in the top 1.2 metres, a fairly indicative sign of non-saline soil. As we ventured closer to the edge of the crop, the readings gradually rose to 85, 96, 170, 192, and finally peaked at 200 millisiemens per metre in the drainage line. Notably, when we hit around 100 millisiemens, we recognise this as a pivotal point in signifying a salt-affected site. Furthermore, the presence of indicator plant species offer valuable cues regarding the severity of salinity in a given area.
So now we're up to 170 millisiemens per metre. So really it's just backing up, as you can sort of see, along as we come down that sort of slope. We've gone from crop to, if like, salt bush, or like a mixture of salt bush and volunteer grasses. Now we're on the edge of the blue bush, and we've gone from less than 100 to 120, I think it was, now to 170. So it's all plants, indicator plants in a way, indicating fresh, indicating more salt areas. I mean, we've typically used Mediterranean barley grass as a salt indicator plant, because that's what is one of the first ones that dominates as you're losing cropping country from fresh country on its transition to become salty country.
It's essential to remember that readings can be influenced by soil moisture status. To effectively monitor a site over time, it's advisable to take readings at a similar time each year, ensuring consistency and accuracy. However, what the DPIRD team has found with repeated experiments on the same transects across Western Australia over time is that the relative reading across the transect doesn't change that much at different times of the year. So whilst the absolute numbers may be higher across the transect at a wetter time of the year, the readings are still relative to the amount of salt in the profile. On this property, the deep drain serves as a vital tool, efficiently channeling groundwater into the valley floor. This proactive measure slows the insidious creep of salinity up the slope, preserving the land's productivity.
And that water, the level of water we can see in that drain is groundwater. That's the groundwater level, and we can see in the far distance it's virtually at the surface, which we'd expect in a saline valley floor. And then as we come back up, that water level, we can see that gets deeper and deeper, progressively deeper, to where we are now. I estimate it probably be almost 1.5, 1.8 metres down, whatever it would be. But if we look on the edge of the drain or out to the side, it correlates really well with the vegetative cover as well. So if like down the bottom, we probably can't see from here, but if like the bare scald where the water's within a 30 centimetres or so of the surface, and then we've got the sandfire area, and then as we're basically losing the water table, or the water table becomes a metre or metre plus below the ground, is where we see that transition now into this the salt bush type area. So again, it tells the groundwater or the drain effectively is telling you the same sort of salt story or same salt affected story. I mean, it's the shallow saline groundwater that's driving the salinity problem, the land salinity problem, and then we can visually here we can sort of see that correlation between shallow saline water table and vegetative cover. And then if we we can't, the drain doesn't go up, but if we extrapolate back up to where the crop is, where the cars are, or the healthy crop is, that I would anticipate that the water level or the groundwater level is going to be 2 metres, perhaps 2 metres plus below the ground. And then really here with this drain, it's exposing and showing us, that's what's causing the salinity problem. That's correlating really well. The depth of saline water table is correlating really well with vegetative cover.
Through careful landscape observations and the use of the EM38 scanner to quantify salinity levels, farmers and land managers can easily gain an understanding of changes in dryland salinity over time. This information serves as a valuable tool in making informed decisions and implementing effective management responses.